All right. Hey everyone, my name is Rushil, and today I'm going to talk to you guys about automated algorithm selection discovery using LLMs. And a quick thank you to my team for making all of this research possible. All right, so a preview of what we're going to go over. So first, I'm going to introduce you guys to SmartSolve, which is what makes this possible. Go some of the motivation, the methodology, and how it sort of works. Then we'll go into the LLM aspect, how we use that to generate heuristics. And then at the end, we'll talk about integrating these heuristics into linear algebra workflows. All right, so why are we doing this? Well, linear algebra problems have many ways of being solved, and each approach can be more optimal for certain inputs. For example, you may see like 10 to 20 times speed up in certain algorithms depending on what input you provided. And there already exist heuristics by current linear algebra packages that attempt to solve this problem by partitioning the input space to certain algorithms. However, the main issue is that the feature space of all the inputs is really, really large because you have to take into account like all the possible matrix structures as well as the hardware, the precision you're dealing with, the algorithm, the format of the data. And so it's really difficult to develop a proper heuristic. And so what SmartSolve aims to do is have an automated approach to generating these heuristics. All right, so how does this work? Well, first we have a discovery stage. In this discovery stage, what we do is we take a list of matrix patterns, which we've gotten from like SweetSparse, Matrix Depot, and other matrix pattern repositories. And then we have a list of candidate algorithms that solve like a central problem. And then we run each of these algorithms on each of the inputs to see what, like, the time that it takes to perform each of the algorithms. We can then store all of this information within a database, a little bit more which I'll go on to later. And then we can have an LLM or some AI agent look at this database and analyze it to determine an optimal heuristic for algorithmic choice. And then lastly, we can take this heuristic and put this in other linear algebra packages so that users who use those linear algebra packages are able to use our optimal algorithmic choice. And an example of how this would work for LU factorization is, so there exist two default algorithms for LU factorization and some more specialized algorithms that work better for particular types of matrix patterns. And so we want to see, how can we choose which algorithm to use to do LU factorization based on the input we provide. And so we can run our benchmarking and discovery process by running each of the inputs for each algorithm that candidate algorithm we're dealing with. Then we can provide this benchmark to an LLM, which will look at this benchmark and determine, okay, now if I have a new input, how should I determine what the optimal algorithm will be? And it will do this by looking at the features of the matrix, information about the precision, and other important factors. And lastly, we would take this and put this into linear algebra software. All right, so what does this database actually contain? So one thing that it contains is the information about the input itself. And since we're dealing with linear algebra problems, this is information about the matrix structure and pattern. And so this would entail, the determinant, the rank, whether it's symmetric or not, just information to understand the structure of our matrix. Then we also contain information about the algorithm and architecture, like the time that it takes to run the algorithm on each input matrix and so on. And here's a quick example of what this benchmarking process would look like visually. And so here we have the Poisson matrix structure, and we run 4 candidate LU algorithms on this matrix structure. And so the default algorithm, which is dense LU, as we can see, it's 10 times slower than a lot of the specialized algorithms. And so if we have some sort of heuristic that tells us, oh, instead of using this default algorithm, let's use one of these other algorithms instead, we can achieve massive speedups, which is important for really large matrices. All right, so now this is the fun part. How do we actually generate the heuristics? And so we're going to utilize LLMs here. So the way we do this is we provide the database as a prompt into the LLM. And this prompt is split up into 3 sections. So the first section is we define the model's role and objective. And so by this, I mean we tell the model, hey, you are an expert at LU factorization. Can you determine some sort of optimal heuristic by analyzing this database. Then we actually provided the performance database to analyze, and then we specify what the output format of the heuristic should be. In our case, we detail it as some sort of decision tree made up of if and else statements for two reasons. The one reason is because it's very readable, right? If I have a bunch of if-else statements, I can sort of tell like what's going on, like how is the model making its decision. The other reason is also fast to compute, right? We don't want computing the heuristic to be a really large overhead. And the reason is, it already takes time to run the algorithm. If it takes a long time to decide what algorithm to use, then that just defeats the whole purpose of, choosing the more optimal algorithm. So yeah, then we can take our heuristic generated by the LLM, put it in some linear algebra system, and then we can pass in the linear algebra features, such as matrix features, such as the condition number, rank, whether it's symmetric, and these will be taken as inputs into the heuristic, which will then decide what the most optimal algorithm is, and then perform that operation. And as a quick example of what this would be, it's a very simplified version is this example here. So the heuristic is simple. We just check to see if it's banded or not. And if it's banded, then we convert the matrix into a banded data format, and then run this banded LU factorization version. Otherwise, we run the default factorization version. And the hope is that checking to see whether the matrix is banded or not, the time that it takes to do that is not as significant to where running the banded version compared to running the LU, normal LU version, there's a huge difference in that time. So if we go back to this graph here, right, we would hope that the time that it takes to check if it's banded is much less than 9 times the amount it takes to calculate banded LU, which it definitely is. Okay, so now let's talk a little bit about integrating our heuristics into the linear algebra ecosystem. So there already exist a bunch of linear algebra packages in Julia. One example is linearsolve.jl. And so what we could do is we could provide these heuristics into functions that users call in linearsolve. And under the hood, when a user calls a function in linearsolve, it will use this heuristic to determine the optimal algorithm and then actually run that optimal algorithm. But this isn't just limited to Julia, because we can apply the same idea to other languages like Python and MATLAB, which each already have their own heuristic. But again, developing the proper heuristic is really difficult to do since, as I mentioned before, the feature space is really large. And so the hope is that by developing these automated heuristics, we can change the whole linear algebra ecosystem by making these optimal choices. All right, so yeah, thank you guys so much for listening. Yeah.
Thank you. So I have a very quick question. Is the output of the LLM heuristic still in the form of decision trees?
Yeah, so the LLM outputted heuristic, it's just a Julia function basically, and this Julia function has inputs as the matrix features, and then the inside the body of the function is a bunch of if-else statements. So it checks if the size is greater than 10, then run this algorithm, otherwise run this algorithm.
I see. So how does this improve upon just using traditional machine learning to form a decision tree and then generate the code?
Yeah, that's a good point. So the main idea is one, customizability. It's really easy to tell the LLM what you want the output format to be, and you can also include it to make it actual Julia code. So you can just take the output of the LLM and just run that as Julia code. Where for a decision tree, it may not be as simple. The second reason is LLMs are evolving really rapidly, and so they're able to detect patterns at a much higher rate, more complex patterns than maybe a decision tree might be able to do. And so maybe it could be the case that decision trees are better, and that's what our current algorithm, if you look on our GitHub, that's what we have right now. The LLM is what I'm working on at the moment. So maybe it is the case that decision trees are much better, but I have a feeling that since LLMs are constantly improving, I think it's a worthwhile investment to at least try LLMs and see how they improve. Yeah, good question.
Hey, A very short question. You said the LLM are getting better. So which one are you using? Which model?
Yeah, so I can talk a bit more about this offline, but right now I'm using Ollama to download like LLM models locally, and when I ran these like efforts, I used Llama. I think I used CodeLlama and Llama 3, but I'm like trying to use other LLM models to see if they perform better. Just trying to figure out which ones are the most efficient.